Okay, my friends, did you know that doctors and medical people do not know what a virus is? They don't know what it is. And this is the National Institute of Health, and this is investigating the concept and the origin of viruses. Now listen to what they have to say. This is the most important thing they say. In this article, we revisit fundamental questions about the nature, origin, and evolution of viruses during this public outbreak, and the virus biology is at its peak. They want to understand it. We emphasize the need to rethink viruses in the light of new discoveries and call for broader acceptance of new views that are resisted by century-old concepts established in early virology research in its early days. Well, it's completely changed, but they refuse to engage. So I am going to present the evidence that shows the only thing that happens in your body that makes your body work is an enzyme. All right, remember that. If you don't have the enzyme, you do not get the chemistry. An enzyme is so incredibly reactive that it does more chemistry in a quarter of a second than would happen in years if left to just do it automatically. And it would actually end up doing it, but it would take years rather than a quarter of a second. It happens at the speed of light. It's called click chemistry. I will explain all of this, and I think in great detail. And I would like to engage with any researchers, any doctors, any lab technicians, whoever thinks that they have a good handle on understanding the immune system. That's the people I want to talk to. All right, so where do all these bacteria and enzymes and all those things live in your body? Where do they house themselves? Well, basically in this layer right here, in this little dark layer, and then they squirt into the fluid-filled highway with their little flagellas to zip, 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 go right back and forth. And that fluid brings the enzymes and the bacteria and all of the waste to wherever it's got to go. That's the fluid-filled highway. And I believe it's also the lymphatic system, more or less. And so these are floating around in there, trying to kill things that are invading you and breaking down food and so forth. Now, those balls, remember, I said, are the ribosomes. Well, where do they come from? Ribosomes come from bacteria. And there's thousands and thousands and thousands, probably hundreds of thousands of species of bacteria in you. A species is an exact type of bacteria. It creates only one single thing, ribosomes, let's say. In this particular case, there's other ones that go out and consume wastes. These spit out ribosomes to go and break things down. And that ribosome is in here inside this single cell. Single cell. It's so tiny you can't even see it. I mean, you can't see even with a top microscope almost. Now, it comes out of here, it gets all built up, and then it packages itself into a ball. And that's the ribosome. Pops out. Now, I don't know if they're just continuously squirting out into the environment, or they're only popped out when they're needed, or there's different types that pop out when they're needed and other ones that are just always around. I don't know. But what I do know is that particular ribosome, when it pops out and it unfurls itself, and the sheath comes off, it turns elegant. Very, very, very elegant. And this is what it looks like. And if it's not exactly like that, it doesn't work. It's called denatured. If it comes out in its natural, perfect form, it works. If it comes out all twisted up and destroyed, it doesn't work. If it's not there at all, well, it's because you don't have the bacteria to squirt it out. There's a series of different possibilities here. But we got to stop and think about what is going on. This is where all that stuff is traveling through that fluid-filled highway to go attack. Say there's an invader trying to get through here. You got to send some troops over there. All right, and that's what the cancer looks just like. It bumps right through your skin like that. Here it is right here. So you can get sores and all kinds of little pussy things going on. But once you go through this layer with certain types of cells, it's cancer and it's all over. Well, it's a problem now because you don't have the right bacteria to fight against it. Now, I would think if you had the right bacteria and put it in, you could actually bring that thing right out of there and kill it. But you'd have to have all the right bacteria to do it. You don't have the right bacteria, I don't care what happens, you're not going to be healthy. It's as simple as that. And here's where all that bacteria lives, is in all of these different places. And this is down in your guts. All right, now this is the esophagus. That's your stomach lining. This one right here is the small intestine. And this is the large intestine. They all have one thing in common. They have a layer here. I believe it's this layer right down in here. One of these layers is where that fluid-filled highway is. It could be this one right here. But what it does is it keeps you from being invaded. So, let's see, what it is? Well, epithelium. It's just below where you're going to be invaded from. That's the membrane that protects you. And that's where the interstitium is. Now, a baby has no digestive system to speak of. They have completely nothing to start with. So they have to build all of their bacteria as they go along. You see right here? This is the digestive system of a newborn. Unlike the adult body, the fetal digestive system does not have a digestive function from birth. They can't digest. The stomach and intestine are reduced, while the liver is proportionally much more developed. The liver deals with toxins. Now, what I got here? Ready to program. Okay, it's ready to program from local bacteria. And the baby should be slathered with fecal matter and vaginal juices and all that when it's born. All right, so that's what's going on. And that's why they're so vulnerable. Kids, very, very vulnerable, especially to being infected by something and not having the right bacteria in them. They can't fight back. They're just getting started. And this is what the guts look like. Here's what's going on. Here's what happens. You eat something, and first of all, it goes down through your throat. And that's something that they don't even think about. But there's all kinds of digestive juices going on up there, too. And in your mouth, and your tonsils and so forth have a certain function. I'm not exactly sure what they do, whether they sense what's coming down there, or whether they add some juices. I don't know. People have their tonsils out, and I had mine out, and it didn't seem to do anything, but I don't know. Now, as you come down through the stomach has all kinds of acid and really caustic stuff going on. So the coating around the stomach is going to have a certain chemistry that protects it from these acids and things. Once you get into the small intestine, and all that's sort of going on in the small intestine, it's a whole different story. It's got a lot of saltiness in there, I believe, as I recall. And there's a lot of absorption of certain types of things here, certain types of molecules that work with that type of chemistry. Then once you get into the large intestine, it's another issue. That one there is where I believe you're digesting most of your food and breaking down all your fiber and all that stuff, and you're absorbing that. It goes into your bloodstream and into your system and into the lymphatic and brings it around through those different charged molecules. Like I showed you, the transition metals have the positive charges and the ligands have the negative charges. This is just nothing more than blood. This is just exactly what's in your blood, is all those metals. They're all the metals in the transition section. Right there. That's why they don't sit here in the periodic chart. They're all by themselves because they have all these different charges. So now, that's what carries things around your body. What else do we see here? There's the fluid-filled highway once again. These are payer patches. These are very interesting because these are only in kids up to, I think, 15 years old, 15 to 19 years old, something like that. I believe these little black spots are bacteria that are floating around in the system here, which you want. You want those. So that you don't get some coming in from the side here. That's the key. Now, you see how this has little entryways going out into maybe this is a fluid-filled highway. I'm not sure. It's one of these spots. It could be this right here. Or it could be this. But these are the payer patches, and that's, like I say, those are only in young kids. Well, 15 years old, up to 15 to 19, I think, something like that. And then this is the intestines. Has all these spikes sticking up through here where all the food comes through and gets absorbed. But it's through a membrane. The membrane says, I let this stuff come in, but none of that other stuff stay out. And that's what it does its job. But if you break in through these things, or you get, some kind of really nasty toxin that eats a hole through one of these, you got to be able to fix it pretty quick, or you're going to be invaded. And if you can't fix it, you have a chronic condition. Every time you eat something that has some kind of, attraction to that spot or whatever, you might just have a continuous chronic irritable bowel syndrome. It just never goes away. And here's what it looks like in actual. As the food comes through here, all these different things are absorbing the molecules. And this is the stomach lining. And of course, like I said, some places are going to be caustic, some are going to be acidic, some are going to be a lot of watery things. And towards the very end of your digestive system, you absorb all kinds of stuff. Right at the very end, you absorb a lot of vitamins and minerals and fluids and so forth. And you can really, anywhere in here breaks through, you're in trouble. And these are the different kinds of digestive enzymes that are in your body. In the saliva, you got enzymes. Gastric juices, pepsins, protein, these are the enzymes that work on the substrate and the products that they create. So there's a lot to understand about what's going on in your body. It's not hard to understand, though. It really isn't. There's a membrane that coats every single organ, every single tissue that's in your body. They separate one from another. And if it breaks through that membrane, you're in trouble. And if you don't have the right bacteria to be living in this membrane to protect you, those are your troops, those are your delivery agents, those are your pickup garbage collectors, those are where your chemists live, those are your frontline troops to invaders, attack invaders. Everything happens in here. And it controls mood, everything, 100%. And then it sends out the products that are being created in the gut to be used, like to insulate your nerve fibers. If you don't have these specific types of products, which are like little rubbery products that coat your nerve fibers, you get all kinds of, and I believe that's where autism is coming from, is that you don't have the materials to coat the fibers, and they're just not working right. They're just shorting out together. And we have had success treating kids with probiotics and some other little molecules which are right in the membrane area. The membrane is a phospholipid membrane. P is the phosphorus. Sulfur, silicon, magnesium. Those three, and the aluminum gets absorbed by silicon from volcanic areas, silicate waters. And somebody else discovered that, and I'm pretty on board with that. An isotope of silica in the water will adhere to the aluminum, and you'll just flush it out of your system, urinate it out. Because aluminum buildup causes problems, they say. Some of this stuff I'm a little shaky on, I don't know. But I do know that your membranes they're made of phospholipids, phosphorus, fatty tissue. Sulfur is right above phosphorus, and it works its way down into the phosphorus. That's a daughter isotope of sulfur brings you to phosphorus. And a daughter isotope of phosphorus brings you down to silicon. And you can also have silicon bring you up to phosphorus. Okay, we might as well get started right from the beginning. I am going to be talking about the microbiome, and they have a transition network now where they're trying to figure this out. This is the U.S. National Science Foundation, and they're talking about 7 degrees from 1 trillion species of microbes. Trillion species of microbes. Every single one of these microbes has a little job to do. And a lot of bacteria, at least a lot, creates enzymes. They are the factories that create enzymes. Now, Global Microbiome Transition Network hints at origins and evolution paths of microbiomes. So they're trying to put it all together and understand what and where all of these different viruses came from. I have a different approach to this, but we need this information. All right, like I said, they want to put together sort of a map of where all of these microbes and which different cultures had which different types of microbes and all that business. So they're going to 20 diverse ecosystems to build a global microbiome transition network. It connects based on their composition similarities all over the Earth. 177,000 microbiomes from 20 diverse ecosystems include the plethora of ecological niches in the human body and the environment. So they're trying to figure out what bacteria lives where in the body. Exactly what I'm trying to figure out too. Now, why are they doing it? They want to put together some kind of big database of how the evolution happened. I don't care about that. I want to know what microbiomes are you supposed to have in your body and what ones are you not supposed to have. Some of them, you're going to have good and bad coming through you all day long. You get bad bacteria going in you 24 hours a day. It's going to be there. You're going to have bad bacteria going in you, but it should not attack you. It should not attack you. Why would it attack you? Why can I eat the same stuff you eat and I don't get sick and you get sick? This is what we have to understand. This is what they're not understanding is this membrane activity, this fluid-filled highway that protects you. This is what we're going to get into. All right, this is Harvard, and this is pretty new. This is only a few months ago. And they're talking about leaky gut, what is it and what does it mean for you? And they said, they call people hypochondriacs for talking about problems with their guts. But no, it's more than that now. What exactly is leaky gut? And this guy is outside his realm, above others talking about this, because others won't speak about it. Now, what exactly is it? Well, inside our bellies, we have extensive intestinal lining, covers 4,000 square feet of surface area. When it works correctly, it forms a tight barrier. It controls what gets into our bloodstream and what is not allowed in. An unhealthy gut lining may have cracks or holes in the barrier, allowing partially digested food, toxins, and bugs to penetrate the tissue beneath it, causing inflammation and changes in the gut flora, normally the bacteria. Now, that's what's happened. The bacteria changes. And the bacteria changes, and that's what causes the cracks and so forth. It's not the other way around. They say the cracks and the inflammation may cause normal bacteria that could lead to the problems within the digestive tract and beyond. Well, it goes all through your whole system because it's this fluid-filled highway they really never knew about. The research world is booming today with studies showing that modification in intestinal bacteria and inflammation may play a role in the development of several common chronic diseases. I say 100%. Every chronic disease is an invasion. It's a slow invasion. If it's chronic, it's not bad enough to totally kill you, but it's still eating away at some part of your body. Now, eventually, it may become so toxic that it will kill you. But, for a while, you can live with these chronic conditions. But why? Why not find out what bacteria is missing and repopulate it? That's what fecal matter transplants do. And I think they should really, really, really start looking into that, because that's the only solution to replacing the bacteria. And it does work. They've proven it works. And there is virtually no side effects. You get a little stomach discomfort for a couple of days because you did put in all new bacteria. But then after that, within a few days, they say it's basically over and you're good to go from there on. You see this? This goes back to 2016. Eat, Poop, and Live. This is Yale University. They knew about this long ago. That's what it says here. They found that these people living in the desert were eating camel poop to fix their bacteria in their stomach. And it says the dung was loaded with the bacterium Bacillus subtilis. The species is the same genus as the terribly pathogenic species Bacillus anthracis, which causes anthrax. So these are very closely related, and one of them is good for you. It says Bacillus subtilis has, however, since become one of the bacteria species considered good for humans. So we need that bacteria to fight off certain digestive disorders. But you don't want anthrax. So they're very close to each other. What turns one into anthrax versus the other? Are they two completely separate? They're in the same species. They're basically the same, but just a tweak different, appears to me. So let's not worry about fecal matter transplants. Let's just focus on what causes the illness. And they're saying how bacteria keeps proteins moving. Proteins are the things that build your body. So you need bacteria to make proteins. And they make them with the ribosomes. And they contain large numbers of negatively charged proteins. They say it's to avoid electrostatic interactions with ribosomes, but I say it's to do this. It's to work with the transition metals that are positively charged. And the transition metals carry these things around. You have the metal core, and they carry around these negatively charged particles, and they deliver them, and they pick something up and bring it back. And they work in, well, here's what it says. Transition metals form colored compounds and complexes. Their colors can vary depending on the charge on the metal ion, which all these are the charges, 3 plus, 2 plus, 5 plus. All right, so it depends on that charge what the color will be. And the number and type of groups of atoms called ligands attached to that metal ion core. So we have all these things that can attach because they're negatively charged. These are positively charged. So that's what I say is the case here. They say that bacteria contains a large number of negatively charged particles. They do. And they give them up to the transition metals. The transition metals deliver them. That's what it looks like to me. But we're talking about ribosomes and proteins. Well, ribosomes create enzymes, but enzymes are the same as proteins. Let's look into that. All right, you're going to stick around because you'll be as trained, I'm serious, as any doctor right now, any microbiologist, anybody that's working in the medical field. You will understand literally more than they do by the time I'm done showing you this stuff. These are ribosomes. They come out of bacteria. When they do, they pop open the sheath, and then they turn into enzymes or proteins or viruses. Viruses are the same they're all the same. They're extremely elegant packages of molecules. And the protein is a building block. Enzymes normally break things apart. They disassemble things. Proteins assemble things. And viruses come in and take over our bodily functions and go against us and break through walls and eat up the products our body is supposed to have, and they cause havoc in the system, the viruses. But they're all the same product from the same thing, which is a ribosome. This is just insane. Listen to this. The cytoplasm, which is the fluid of a bacterial cell, is densely packed with DNA, RNA, and various proteins and macromolecules. In this particular type of E. coli, for example, the cytoplasm, which is the fluids, is home to around 2 million soluble protein molecules. 2 million in a cell. This is estimated using a certain database, and about 55,000 ribosomes. We're going to be going through ribosomes. We're going to go through everything, so get ready. Don't forget, that's in one single cell, and it is a single cell. That's all it is. It has all that stuff inside of it. All right, remember this. Better said, bacteria are the factories that produce enzymes. Bacteria produce the ribosomes, which end up being the enzymes, the proteins, the viruses. And then it says enzymes are not alive. They're complex chemicals produced by bacteria. They can't produce by themselves, reproduce. So the bacteria can, but not the enzymes. And they actually can't consume waste. The bacteria can. They speed up chemical reactions without getting used themselves. That's the click chemistry I talked about. Click, and it all dies. Click, all that stuff dies. That's the click chemistry. Now, these enzymes are extremely exotic, and they need to be produced by a bacteria. You don't have the bacteria, you will not get the enzyme. Simple as that. You see those little balls I was showing? Those ribosomes are large, in the molecular world, complex enzymes. Their ribosomes end up being enzymes. When they come out, they're in the ball. When they disassemble, they become the enzyme. Now, what about viruses? Ribosomes are protein synthesized factories in cells. Viruses need those to manipulate ribosomes to complete their protein synthesis. So it's involved with the ribosomes as well. Now, where did the ribosome come from? The ribosomes come from bacteria. All right, you see this right here? Bacterial enzymes. Bacteria create the enzymes that are responsible for degrading, breaking apart proteins into their component amino acids. So they break them down into their little building blocks, and then they can build back up. Process is known as proteolysis. Proteolysis occurs at a different rate for different types of proteins present in the body. That's the catalysts. Those are the enzymes, and they occur at different rates. You need different breakdowns, but they're all different types of different breakdowns. So it's not, they may be right about that. I don't know, but I do know that the enzymes, they work at the speed of light. Some of them may not work that fast, but I believe they do. Virtually all of them. All right, remember I talked about click chemistry? Let's say that's the invading molecule, and they're very elegant like this, and it's getting through your system. What you're supposed to have is an enzyme, which is one of these very elegant molecules. All right, now every one of these has magnetic signatures. There's a magnetic signature all over this. Hold on one second. All right, this is the magnetic signature. It's exactly got to be like this, and every one of these is a magnetic dipole moment all over this thing. So that's its signature, and it's built solid. They don't break apart. They come up and they find an invader, and they go click, and this thing goes blip, and it's all over. It's dead. Case closed for that guy. And this guy just keeps going along, and he finds another one. He goes click, and that one dies too. That's the beauty of an enzyme. It doesn't get worn out. It keeps going on, bang, 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 bang. And eventually it gets consumed if there's nothing else to bang into. All right, here's the key. These are phospholipids. See this phospholipid bilayer? Well, lipid means fatty. Phospho means phosphorus. So you got a lot of phosphorus, and then you got fats in here. And that is the membrane that protects you so that nothing can get through there that isn't allowed. These are the protein channels. Remember we talked about the proteins, the charges, and so forth. They will allow things in here, but only if it's the right thing. Otherwise, you stay out. Now, these phospholipids are right here, P. Sulfur is right above phosphorus, and it degrades down to phosphorus. There's a lot of chemistry right in this exact spot that controls your membranes. And we've been studying the chemistry, and the sulfur seems to, the daughter isotope of sulfur is phosphorus. Okay, this is too much. This is shocker du jour on steroids. These are isotopes of silicon. Now look what the isotopes of silicon are. If you go, of course, these are all different silicons, they're different weights. Now just so you understand, electron flood theory fixes everything in physics, in subatomic physics, fixes it, no problems anymore. But what you have to understand is that silicon is not just one big, like they would consider silicon to be like this. All right, and it made of a bunch of different protons. But every proton would only have like 3 quarks. You can't have all these different isotopes with that. It's just impossible. You have to have a bazillion different little particles. There's no way they can account for the isotopes, none whatsoever, until you get into electron flood theory. And here's how it works. This is silicon without enough silicon in it. So we're down here. All right, silicon 22. Listen, look at the weights. You see the mass, the weights, 22, 23, 24, 25, 25, 26, 27, 28. By the time you hit 28 right in here, you're stable. So what does that mean? We just added another one, another one, another one, coming up the line. Until we get to 28, we're stable. All right, so at 28, we don't want to give any up. We don't want any more coming in. Now, you take the alternative to that is where we're going to get all our phosphorus from. Look at this. Now, this is interesting because how do we get silicon into a state where we're going to get the daughter isotopes of phosphorus? Look at all that phosphorus. Now, these are silicon 31, 32, 30, 28, 29, 30 are the stables. You get above that, so we throw a couple more in here, and we get up to this, and 17, 18, 19, 20, 31, 32, 33, 34, 35, 36, 37. They're just heavier and heavier until you get up way up here where you have just a ton of extra particles on. And you're up here, silicon 44. But look at all this is all phosphorus. That's the daughter isotope. That means that as it breaks down, you're turning this stuff into into phosphorus, which I believe has got to be good for you. Your entire body is coated with phosphorus. It's phosphorus membranes, phospholipid membranes. So that's what I'm seeing is something to look into at least. So silica water possibly is good. I don't know. I do know that I'm doing some experiments right now with silicates, and they turn hard. Now, I don't know if they're good or bad for you. I really don't know. But I know your membranes are made out of phospholipids. And when you go on the other side of that, you get into your aluminum and magnesium. All right, so that's a shocker. I didn't expect to see that. It's all phosphorus almost. You know, this is the beauty about going back through and trying to explain what I'm saying. I start to understand it better myself. I mean, I didn't expect to see that. Look at this. This is all phosphorus coming out of silicon, which is the daughter isotope. Just so you understand, the daughter isotope is what's left over after the decay. All right, they're talking about radioactive decay, but that's not the case. We're talking about using enzymes and attacking the silicon and creating these daughter isotopes of phosphorus. but you have to have the right enzymes to attack the silicon. That's why they have these half-lives. It goes, done, and you end up with phosphorus from the silicon. Now, silicon is one of the most, it's everywhere, so I don't think you need any special silicon, but maybe you do. Maybe you need something that's an isotopic silicon in water, that when you drink it, it right away gets broken down into phosphorus, or broken up into phosphorus, or however you want to look at it. But that's a shocker. Wow, this is a shocker. Like I said, this is the beauty of doing research. You get these chills. Silicon makes up 27.7% of the Earth's crust by mass, is the second most abundant element. Oxygen is the first. So you have to breathe, and then you consume all of this silicon. If it's that much silicon, you know you're eating silicon all the time. There's got to be a ton of it everywhere. Now, here's the key. How do you make that silicon bump up to the phosphorus? Right? Silicon's here. How do we bump it up to the phosphorus? Well, it's got to get attacked by some kind of an enzyme. And then what the end up product will be is that daughter isotope of phosphorus. And what does the phosphorus do? It's probably, I don't know how much of it is in the human body. Hold on a second. All right, another interesting tidbit here. About 85% of the body's phosphorus is in the bones and the teeth, so for structural support. Now, phosphorus is also present in smaller amounts in cells and tissues throughout the body. Phosphorus helps filter out waste in the kidneys and plays an essential role in how the body stores and uses energy. It also helps reduce muscle pain after a workout. Well, phosphorus is in every membrane in your body, and there's 100% of your body is coated with membranes. Look at this. Phosphorus, the second most abundant mineral in the body. Second only to calcium, which is all your bones. Phosphorus makes all your membranes. All right, this is absolutely critical to understand how important phosphorus is. And I'm starting to understand it better now myself. Like I say, I'm learning just as you are. Now, what is phosphorus? Well, we know it's a chemical. And here's the most important thing, is what does it do in your body? Helps form membranes for our cells, for everything in your body. Your whole body is coated with membranes. I mean, there's just thousands and tens of thousands of them. Now, phosphorus is also needed for the production of phospholipids, which is those phospholipid membranes, an important type of fats that make up the structure of our cells. They are the membranes and play a key role in the good functioning of our nerve cells and brain. We need to get more phosphorus in our, well, let me put it this way. There should be a certain amount of phosphorus that is required. And apparently, as I told you, I see no other way for anything to be converted and become a daughter isotope from silicon than to have some enzyme break it down and turn it in to phosphorus. And that was that, well, this is a phosphorus in the human body. What do I have? Anyway, it's really looks like this is an important thing that's being overlooked. I didn't realize how important it was. And it appears to have something to do with silicon. The daughter isotope of silicon is just phosphorus. I mean, it's just saturated, all phosphorus. Okay, this is the membranes, and they're basically all the same. They're two layers with a fluid-filled highway in between, fatty acids or fatty lipids or whatever you want to call them. I think they're fatty acids, but I'm not sure. They are fats with phosphorus. Hold on a second. All right, yeah, they are. They're fatty acids. They're derived from fatty acids. And they're a class of lipids, which are fats. And the molecules have a hydrophilic and a hydrophobic end. One of them repels water and one of them attracts water. and they come from these fatty acids. All right, so here's the key. Let's focus in on this. Glycolipids. That's lipid with carbohydrate attached. These are phospholipids, which apparently are just fatty acid phosphorates molecules. Now, I find this interesting. Is this right here? Is enzymes. Now, what are we dealing with? Lipids, fats. Where'd that come from? Lipase. Now, I'd have to look into this a little bit. But then we also have lipase down here from enteric juices. That's lipids. Lipids from the pancreatic juices. Now, how do you work with that? I don't know. Does it mean anything? I don't know. But these are fatty acids. Lipid from pancreatic juices. Now, same thing down here. Fatty acids from enteric juices. It's just something to consider. Now, the other thing that I missed mentioning, the most important thing is, all of these different places secrete different products. Now, they say they look like they're the same things, lipids. Well, I'm sure there's some differences in the chemistry there. They're fats, yes. They're proteins, yes. They're starches, yes. But they're not going to be all exactly identical. So, these particular organs create juices and proteins and enzymes and bacteria and so forth. They have to live there to do that. So the bacteria is resident in these different areas, and they may be all different types of bacteria, and I'm sure they are, because there's different caustic and acids and, all kinds of different chemistry. And every organ has to be protected with its own membrane, and that membrane is subject to the chemistry inside and outside. So it's going to be a very specific membrane in my mind. It's going to have some kind of chemistry going on there that's going to be different from its neighbor, who might have salts and I might have acids. So what does that mean? It means we're back to the same thing. You have to have the right the right bacteria in the right places. If you don't have them, you're not going to produce the chemistry. And that specific chemistry and that specific bacteria has to live in that specific area to do that specific job, or somebody's going to invade. Somebody's going to come over and take over the property. Okay, I probably went over all this stuff before, but this is a refresher. This is your organs. You digest stuff. It goes through your stomach, your small intestines, and then your large intestines. And they have different jobs. They have different chemistry. They have different membranes, and they absorb things. Once they absorb it, it goes into the fluid-filled highway. And that's why this is so important, is the gut. All right, think about this now. There's 27% of silicates so basically you're loaded with silicates. Now, you got to convert them into other things. What does that? Enzymes do that. And where do the enzymes come from? They come from the ribosomes. Where do the ribosomes come from? They come from bacteria. You don't have the bacteria, you don't get the ribosomes. You don't have the ribosomes, this does not happen. Which is this. The ribosomes do not unsheath, they do not create enzymes, they do not create proteins. So you have to have the bacteria before you get any of this. All right, so what does that mean? That means you don't have the product in your interstitium layer to protect you. That enzyme does millions of, it's so unbelievably fast it reacts, and it reacts at the speed of light. Click chemistry, as I showed you before. In a quarter of a second, this one single enzyme can click and create thousands of other molecules that are attached together and kill them all instantly, because of it just like turns off a magnetic switch. and then it just keeps going down the road, killing the rest of them. And then some other bacteria come in and they eat them up and gobble them up and carry them down to the lymph nodes and deliver them to be flushed out of your system. It's a very, very cooperative system, but you have to have the guys to do the job. You got to have the bacteria to go out and pick up all this garbage. And you got to deliver it to the lymph nodes, and the lymph nodes have to have the correct chemistry in them to break down all of this garbage you're bringing down, especially if you're taking in a lot of toxins and you can't deal with it before it gets into the system. Once it's in the system, and your lymph nodes have to deal with it. With the lymph nodes, you get lymphoma, lymph cancer. And, that's dear to my heart at this moment. I have a friend, somebody very dear to me that's going through this. And, I'd love to try with this fecal matter, something like that, but they won't allow it. They just don't allow it. And everything I'm showing you, and not a single thing in your body happens without an enzyme. Your organs make nothing. They make nothing. They make nothing. They are there as like machinery. And if you don't have the bacteria there inside that machinery to run the machines or do whatever they do with the machines to create the product, which is the enzyme, you don't have the bacteria, you don't get the enzyme. I can't say it, I've said it 1,000 times. Without the enzyme, you don't have any chemistry. There's no chemistry that happens in you whatsoever, none, zero. Without an enzyme. Not a single thing happens. What you put into you would go right out the other side of you, never change. Enzyme does 100% of the work in your body, 100%. And now we've seen, it looks to me like we need to take a new look at silicon and enzymes and what creates phosphorus for these phospholipid layers. I mean, this is all phospholipids. And I'm sure there's some very interesting chemistry with this, because this is all acids. It's the bacteria is making all the products to make like this fireproof. This is like fireproof, you know what I'm saying? This is nasty. Your stomach does some really serious stuff. And the same in your intestines. And all these little things are sticking out into the poop to ingest all this different stuff. And I'm sure this, you see this stuff here, it just looks like, I don't know, it could be poop for all I know. But I also think it could very well be something that's doing some chemistry here as well. As this stuff moves in, some chemical breakdown and gets it ready to be ingested, something like that. But I don't know. It's pretty cool looking one way or the other. Okay, like I said, you're going to be smarter than the average doctor. Very, very few of them understand the significance of the fluid-filled highway and the delivery of the enzymes, and how this fluid completely saturates everywhere in your body. Every membrane has this fluid-filled highway. Even the cell membranes of your red blood cells have a membrane around it, just like this. Everything has to be protected from what's on one side and maintain what's on the other side. That's the way membranes work. Every muscle, every tendon, every fiber, every nerve fiber, everything has a membrane around it. I don't think your doctors will know about nucleophilic substitution and invasion either. They might. But these are the charged particles that are in your blood. These are the transition metals that flow through your blood. And they charge and they latch on to those negatively charged proteins to drag them around your body to deliver them. I don't know how important it is to know that, but I doubt if they do. I'm sure very few of them understand that bacteria are the only things that are capable of making enzymes. Bacteria are the factories that produce enzymes. enzymes aren't alive. They just won't keep growing by themselves. You have to have the bacteria there. Once you take antibiotics or some kind of bad chemistry comes into your body and kills those bacteria, well, then you're in trouble. And they're complex chemical produced by bacteria. Okay, I think I probably didn't state this correctly. There's ribosomes and there's ribozymes. The ribozyme is the enzyme. Zyme, enzyme. The ribosome was the ball. The ribozymes are found in the ribosome. So that the ball is the ribosome unsheaths to show the ribozyme, and the ribozyme is the enzyme. All right, so what is the bottom line to all this discussion? We need a bacterial database that tells the story between healthy people and unhealthy people, or different conditions versus different deficiencies or excesses of bacteria. Now, they claim, they do say everybody's sort of got the same bacteria. Well, yes and no. A lot of people have had some kind of medical intervention with antibiotics or something like that, which damages their immune system. It kills the bacteria. And once you had it, now I had antibiotics after for a root canal. They never said anything, take these, oh yeah, you'll be fine. And then I had to have surgery twice for an anal fistula. And that means it broke through the wall of my anus because I didn't have any more good bacteria down there to do the job of protecting me. And thank God I had a good doctor the second time, because you can go incontinent from having, some of this stuff has devastating consequences just because you don't have the right bacteria. You don't have the right bacteria, you're going to have digestive issues. You have digestive issues, it means your digestion's not working. Your digestion's not working if you don't have the right bacteria. It's basically as simple as that. If you can't create the right enzymes to break down the foods, to give you the products, you're done. If you don't have the right enzymes to attack invaders, you're done. If you don't have the right enzymes to build proteins, your body doesn't get work. It's simple as that. This guy right here ends up creating these guys right here. These guys right here do all the work. That's the only thing in your body does any chemistry. All the organs are there to give you the plumbing to work with that stuff. But the bacteria is there to actually create the products. All right. Otherwise, it's just blood vessels and tubes and all that stuff. All right, so we need a database, and then we need to have people, the National Science Foundation and the CDC and all that, to reconsider this ban on even trying testing the fecal matter transplants. They're not trying to actively investigate this. This has been going on for many, 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 many years. They've known that this stuff works. And I mean, they've known it since the dawn of mankind. But in the last 20, 30 years, they fully understand that it's related to the microbiome. Now, okay, my friends, let's just leave it at this. This is the Microbiome Transition Network, and this U.S. National Science Foundation. I hope they take a look at what I have just presented, and because this is all about these trillion species of microbes. Every one of them, the DNA in every one of those creates the certain ribosome, which creates the ribozyme, which is the enzyme. All right. I love you all. Watch this a couple times. Pay attention. You'll learn, like I say, very few doctors right now know any of this stuff. They're told if you hear a symptom, here's what we use to cure that. If you hear this, here's what we use to cure that. And I don't think they're doing much research investigation is what I'm getting at. I've talked to a lot of them, and they just, in my mind, are clueless, absolutely clueless. I don't mean that nasty. I just mean it's a fact, and they're scared because if they say something and a patient says, "Well, he said to do this," well, the guy's destroyed. So they say, "Oh no, I worked within the guidelines." And that's what it is. Everybody's within the guidelines now. I'm a researcher. I don't say take this, don't take that, but I'm going to tell you right now, everything that I can find that happens in the human body, 100%, 100% involves bacteria and enzymes. All right, I love you all. I hope you all stay safe and healthy, and don't forget the digestion. That's what it's all about.